Hello everyone, I'm welcoming you all once again to this channel. So today I'm going to start a new video tutorial that will be on Quantum ESPRESSO. So here what we will do, we will try to do certain structural optimization and other further DFT calculations what we usually do with other different DFT codes like VASP or Gaussian. So here also we will do the same thing, and for doing all this calculation in our Quantum ESPRESSO, so I will be using this BURAI software that you know, which is the GUI for the Quantum ESPRESSO. And here I am opening that software, that here I am typing this command BURAI, and this is the interface of this BURAI, that is a GUI of Quantum ESPRESSO. You can see it here, and there are some like initial files are available over here. So first one is the silicon CIF, so I am clicking on the silicon CIF. So as you can see that this is our silicon CIF crystal structure, which is visible to us in the screen. And now, so what if we want to do certain things over here? So before going for any calculation, let's first see what are the other features that are provided to us by this BURAI. So here you see that here we are seeing the cell parameters. So this is a kind of BURAI lattice, which is a simple cubic, which is written over here. So if you want to change this crystal structure from simple cubic to any other, then you have the option here. So if I will click on this FCC, you see the crystal structure is now looking like this, and this is nothing but the FCC for silicon. And next if I am clicking on the hexagonal, so the structure will also here this is for BCC and this is for trigonal. So this way you can change. This is for tetragonal, and so whatever the possible possible different BURAI lattices are present for this silicon, that can be only visible to us. And this way you see that these are not visible because we have not provided the other two cell parameter, that B and C are empty. That's why it is not showing us proper orthorhombic. So and now I am coming back to simple cubic. So this way if you want, you can also redesign your crystal structure depending on the lattice vector, lattice you want. Okay, so now after this cell you can click over here. You see that there is there is a section for elements. So I am clicking on this elements. You see that here the only element is what, that is the silicon. There are no such other elements are present. That's why only silicon we are seeing here, and the mass of silicon is 28.08, and this is the pseudo potential that we will come to next. And after that you can see that based on the pseudo potential, we are having this PP type is NC PP, exchange correlation, exchange functional is 2 PBE, cutoff for wave function is 25, cutoff for charge is 225 Rydberg. So this way we have got some of the predefined parameters when we are having this pseudo potential. Next part is seeing the atomic section. So here the atom section is suggesting that these are our elements. So to make this unit cell, this simple cubic unit cell for silicon, we need to have 8 silicon atom. So for all these 8 silicon atom and their respective coordinates are given in this atom section. So this way you can see, like if you want to change certain atom, or what if you want to do a doping kind of thing. So here if you want to dope any other element, so instead of the silicon you can type simply one name. So now you can see that instead of this silicon, this carbon atom came here, because I have modified the silicon to carbon. So this way also we can do. So various modifications are possible using this software, that we will see in our upcoming videos. So after that, what we will see, that what are the other options are available. So okay, let's go and see that. Here is the another option on the right corner, that is the geometry. So if I am clicking over here, you see it has started from geometry, SCF, optimize, MD, DOS, band, NEB, TDFT, phonon. So these are the options are available to calculate anything using our BURAI software. And also if you will see on the left panel, like on the left corner, there is another options are available, like results, run, screenshot, designer, save as, save, modeler, input file, so atoms. So many options are available, and in today's video we will go one by one. Okay, so here our aim is to do the SCF calculation for this particular crystal structure of silicon, which is of simple cubic type. So here I am going to this geometry. Now I am on geometry, and our first thing is to check the input file. So on the left corner I am clicking on the input file. So here you see this is the input file, which is like the very simple input file which has been written. Like here you see that the pseudo potential directory is this one, and from that directory it is taking the pseudo potential file of this one, ultra soft potential. Next, this is the lattice constant, this is eyebrow-wise lattice, this is number of atoms, and the type of the type of atom. Here only one type of atom, and we are having eight silicon atom, so everything is written over here. And these are the atomic positions given in the angstrom unit. Okay, next part is, what if we want to see the what are the other pseudo potentials are available, so that we can see. So I am clicking over here. You see that under this element section I am clicking on the pseudo potential. Here you can see that the pp type is written to all, and exchange correlation functional is all. So what if I will so here you can see that many of such such pseudo potential files are appearing. But what if I will make this all to power potential and this exchange correlation to pbe? Then you see only these two options are available. So these are almost same. Like if you will compare all these informations which we are seeing right now to the other one, these are almost same, but there is certain difference. This n is standing for something, but this nl is for non-linear. So based on our approach and what kind of calculation we want to do, we have to select our pseudo potential. So right now I am making it to all. So these are the different pseudo potentials which are available. This is with power potential, this is with ultra soft, and same exchange correlation functional, that is pbe. So this way you can choose your pseudo potential, and for us this the default one is this one. So this last one was the default one, but what if we want to change? We can also change to this ultra pseudo potential. I am changing right now, and I am clicking it here. You see that now this pseudo potential file is changed to this one. Okay, next part we will go to the, so right now we are in geometry, so now I am going to the SCF part. So here what are the options are available? You see that here options is like standard settings, like restart mode. If you want to restart, sometimes what happens, our simulation gets stuck over at some point. So if you want to do restart from the output file from there only, so you can also do this, that we will see. And this is if you want to calculate the force. If yes, then you have to click on yes. So like this you have to do. If you want to calculate stress, then you have to do yes or no. And then this is the cutoff for wave function, and this is a cutoff for charge. That, like, these are the default value related to that particular pseudo potential file. Next is k point. So if you want to use symmetry, then you have to do yes or no based on your necessity. Next is the k point. So the k point, so by default is set to be 222. If you want, you can increase this to 333 also, no issue. Okay, now this occupation is smearing type, and smearing here is Gaussian type. So I am returning this smearing and everything up to the default value. And also this k point also I am making it to 222, so that our calculation can converge easily and converts faster. Next is the electronic optimization parameter. So here you see that there is maximum steps. The steps in by default is 201. So if you want to increase, if your system is quite big, then you can also try to increase this number. And this is threshold for the convergence. Then this is the initial wave function that we are guessing. We can guess it for atomic, or we can guess it for atomic or atomic random or random, anything you want, but atomic plus random will be better option to choose. And the initial guess for charge density is for the atomic, because we want to do the charges, like the charge density calculation for all the atoms. And next part is the magnetization, so which we don't require for this time. And GGA plus U, that also we don't require. Now you see that our earlier input file was something different, but now this is a very detailed input file has been created, as we have set our different values. So here this is updated. Now you see the guess, this is the cutoff wave function, cutoff for charges, everything is written right now. Now the calculation type is SCF. And next is the smearing type, everything is now written over here. And next, the electronic maximum step is 200. So and this starting point for charge density, starting point for wave function, everything is mentioned over here. This is the K point. And next, here you can see that the pseudopotential file is now updated to the one which I have selected. Okay, so this way our input is now built. Also, if we want to do check that whether your system is maintained the periodicity or not, so here you can see that this is our crystal. Now from this modeler option, I am going to change this A vector. So you can see here, so as I am going forward, this A vector it is repeating after the boundary. That means our system is periodic along A direction. Similarly, what if we will check this along B direction, so you can also see the same system is repeating along B. That means it is also periodic along B. Then to check along Z axis, I need to rotate this so that we can see our Z axis. Okay, so here I am going to increase this along Z. You see that it is also repeating along Z. That means our system is a complete periodic along all the three directions. Okay, that's why we have taken our K values equally along three directions. So now this part is fine. Next is what? So do you want to reflect this model in the input file? No, we want to have our original model, whatever we have choose. Then next is input file. So our input file is done. Now also before going anywhere, so here I can show you this designer part. So this designer part is our normal thing. So here what we usually do, so what if you want to change this interface, like this whatever you are seeing over here, like how to like here is the atomic model. So what if you want to change this ball stick to ball model? So you see that this kind of atomic model you can do. Only three options are available. Next is the background colors, that is also you can change. So here I am changing it to white color. Now you see that this is how it is looking like right now. And I can also come to the default value. Okay, so next is what if you want to change the font color. So here the silicon is written like black in color, so we can also change this color. So now it's in purple. So okay, so these are the things that we can do. And also if you want to show the legend, yes, now I'm doing nodes. Now you see the silicon is went out. So axis, so here the axis is showing, so I will do no, then it vanished. So this way you can do certain like kind of modification to your like visibility. And next is this atomic color, that also you can change by using this one. And so here the atom is silicon, not carbon. So I am changing this color to blue color. So now you see this carbon, this color is changed now. So this way you can little bit play around to make your input or like your graphical designing. Okay, so fine. Next is what we will do. Yeah, this was the original where yeah. Okay, this is the atomic radius. If you want to increase this, you can also do increase. Now see the difference. So this way we can do the designing part, and we can control this from here. Now what if you don't want to show the cell? So these are some of the options that you can also check before before saving the exact structure or what you want to show in your original paper. So this way you can do the designing part. Okay, now after doing all this, let's go and run the simulation for the SCF calculation. So here I am going to the run, and here it is showing the job type is SCF. As we want to calculate the SCF, here are certain other options are available: optimize, MD, DOS, band. So here we are interested to do the SCF calculation. So now save this project. So I am saving this project here by the name silicon. Save it now. Okay, so here you see the simulation is running, so this red color is appearing. So as the simulation is over, the green color it showed green color. Now go to recently used. I am opening this SI now. Now we will go and try to analyze the results. So I am going to results. Now here I will click. You see that this is the SCF iteration. Only 4 iterations were done, and the SCF is converged, and the total energy is this much, which is in Rydberg unit. Next I can also see my input file. This is my input file, and this is my output file. So at the end it will appear as job done. See here, the job is done. That means our simulation is over, and the simulation was terminated at this time and today. So this way you can analyze, and also there are some various like total energy, all these like informations are available here, and this k values, everything is available over here, that you can also see. This is the Fermi energy is also given here. So this way we can check our we can analyze our input and output files, and we can see how many iterations has been done to optimize this silicon unit cell. So this way we can do our calculation. Okay, so I think this much is enough for today. So in the further videos I will show how to do other calculations also using this BURAI, so like using this Quantum ESPRESSO and BURAI GUI. So I think this much is okay for today, and thank you all, and bye bye.